generalize from East from University of Côte d'Azur with Ludmil, who is now at Stony Brook, who has given the talk on Nonabelian Hodge theory.
Okay, thank you very much. So thank you very much for the invitation to speak. So it's a pleasure to address this audience, and also, as some of you may know, we just finished earlier this afternoon the conference in honor of Ludmil, Katzarkov, and Tony Pantev, so my talk is also constructed a little bit around some work that we did in the late 1990s. So I'd like to just start by just recalling usual Hodge theory. So the goal is to discuss non-abelian mixed Hodge structures. You might say the conclusion is that we don't really completely understand what this really means, basically. But we have a number of examples and things like that, and so that's the goal to discuss that, and some sort of directions to what this might mean. But I don't feel that we understand this fully yet in any case. So maybe we'll see at the end of the talk kind of recent directions that show the type of thing that might be happening. But so let's just start with usual Hodge theory. Okay. What you would call abelian. So the setting is, suppose we have X, smooth projective variety over the complex numbers. So this means it's given by equations, polynomial equations in projective space. And if we say smooth, that means that it's going to be it's going to give us a smooth complex manifold, a smooth and compact. It's a Kähler manifold, and the Kähler form. There's lots of different possible choices of Kähler form, but one choice would be the restriction of the Fubini-Studi. Form. So you can read all about this in Griffiths and Harris with equations and everything. But this is important because it gives us this is really the key to getting any kind of Hodge theoretical information from this. Well, so you know there's two different types of topological spaces here. There's the algebraic variety, which is the Zariski topological space and so on, with some prime ideals and that kind of thing. Then there's the usual topological space, which is just you look at the complex manifold Pn, which has homogeneous coordinates x0 up to xn, but you say that two ones that differ by scalar are equivalent. This is C n plus 1 minus the origin divided by C star. You just take that as a manifold, and then if you look at the solution set of your equations, then that's a subcomplex manifold, and this smoothness condition means that it's a complex manifold instead of some kind of singular space. And so in particular, we get X top, which is a topological space. So for example, P1 top is this two-sphere, okay? And if X was a curve of genus G, then it's a topological manifold of genus G. Okay, so now what are we trying to study? So we would like to study the topological invariance. So the first one would just be the cohomology. We might say with rational coefficients, for example. So this is going to be a finite dimensional Q vector space. And what does Hodge theory say? Well, Hodge theory tells us that this has some additional structure. So Hodge theory gives us what's called the Hodge decomposition. If it's going too slow, or it'll speed up a little bit later. If it's going too fast, if anybody has questions, please stop. Okay, so the Hodge decomposition is, we take this thing. And for example, by this I mean like you could say singular cohomology or check cohomology or something, or you could just take the homology and take the dual if you want. So this is kind of an important point here, which is that Hodge, the information we get from Hodge theory, it's happening on a complex thing. So it's happening on a complex vector space. And the Hodge decomposition is that this is a direct sum of HPQ. There's really only one index in this direct sum, but we usually use two indices for reasons which might become clearer later. So it's a direct sum over P plus Q equals I of things called HPQ. And what's HPQ? So HPQ, which is isomorphic to what I'll call a script HPQ, it's a space of, let's say, Durham cohomology classes that are represented by harmonic forms. Okay, so this scalar metric, which I said here, that's a two-form. That's a closed two-form. But it corresponds to a metric, a Riemannian metric. So you use the Riemannian metric G to make a Laplacian. And then the solutions of the Laplacian are called harmonic. You make a Laplacian on each of the forms of degree I. Solutions of the Laplacian are harmonic forms. And so the point is that the Laplacian actually respects what's called the Hodge type of the form. So this means that our form is going to be, let's call it maybe alpha, is going to be written as an A, I, J, dz, I1, dz, I, P, dz bar, J1, dz bar, JQ. And so what are these? These are Z1 up through Zn are the holomorphic coordinates on X, locally on X. And the Z bars are the complex conjugates of that. Okay. So you know if you're right. If you write your holomorphic function as a sum of two real functions, x plus iy, square root of minus 1 times y, then dz is just this, and dz bar is the complex conjugate. let me not write this on down, but remember that when you have a holomorphic function, it means that if you take d of it, a function being holomorphic means that if you take d of it, that's a form of type 1, 0, not, that has no 0, 1 part. Right, the 0, 1 part, that's the del bar operator. That's the thing that kills the forms. Okay, so what should I see? So one of the basic facts is that the Laplacian preserves the Hodge type. This is called the Hodge type of the forms. And so so the solution sets of the Laplacian decomposes it according to the PQ. And you have the C infinity, the real C infinity Hodge theorem that says that DRAM cohomology classes are represented by harmonic forms. Okay, so combining those two things together, you get a decomposition like that. That's called the Hodge decomposition. And this is an invariant of the complex structure of X. Okay. But this is going to tell us some stuff because, for example, just from this description, it's relatively easy to see that HPQ equals HQP bar, right? So if you think about it, that immediately tells us that if I is odd, then the dimension of this space has to be even. So that's already something which is not necessarily true for a general complex manifold. This depends on the Kähler property. The fact that the Laplacian respects the decomposition of forms. The fact that the Laplacian represents this thing, that's a consequence of the Kähler property. And if you like it, this comes from the fact that the Laplacian is equal to twice the del bar Laplacian. Okay. Let me not go into Laplacians, but okay. I mean, if you've seen this before, then this is a reminder, and if you haven't seen it before, probably just stick with this this fact would be good. Okay, so now we have a couple of other different ways of expressing the Hodge structure, expressing the cohomology. So we have what's called DRAM cohomology, algebraic DRAM cohomology. So algebraic DRAM cohomology, that's going to be, we'll call it HI DRAM of X. This is going to be defined to be the hypercohomology of X with coefficients in the complex omega dot X with the differential. Okay, so omega dot X this is the complex of sheaves of holomorphic differentials. I should probably put it in parentheses, algebraic here. Okay, so you can do this in the world of the complex manifold, and you can take the hypercohomology in the world of the complex manifold. And it turns out that this is a complex of vector bundles. A complex of algebraic vector bundles on our variety. Which, if you're talking about the sheaf of holomorphic forms, that's the locally free sheaf of holomorphic things that's associated to these algebraic vector bundles, and the D is a differential operator. You can make sense of what this means in the world of algebraic vector bundles. So one of the things that this means is that if X is really defined inside some P and over some field K for some subfield of the complex numbers. So in other words, the coefficients of the equations of X are in some field K. That's always going to, I mean, the coefficients of the equations of X are always going to be in some pretty small subfield, I mean, big, but relatively very small, because there's only finitely many equations. That's like Noetherian property and so on. There's only finitely many equations, and each equation has only finitely many coefficients. So there's only finitely many numbers which would be coefficients of the equations, and you can just take the field generated by those numbers. It's definitely much smaller than the complex numbers. Okay? And then this vector space, let's call this xk, right, is a k vector space. And then you know, hi gram, then we'll call xc is sort of xk cross over spec k with spec c. This is a complex variety. It just means that you take your equations with coefficients in k and forget that they were in k and just think of them as equations with coefficients in c. Okay. So then we can, but these vector bundles, they'll be defined over k if we look at the world. If k is the field of definition of x, these things will be defined over k. The differential is kind of canonically defined. It's also going to be defined over k. And we can form this hypercohomology. So something I'm sort of not saying here is that there's a Gaga theorem which tells you that if you do this in the complex manifold world, or if you do it in the algebraic variety world, you get the same answer. That's you know, based on Serre's theorem and so on. Let me not write that down, but anyway, there's that thing. But so we have a k vector space, and then hi gram of x, of the complex x, is just the extension of scalars. Okay, that's just to give you an idea of the kind of the nature of what's going on here. So this is, I'm just trying to say that this is something which really depends completely on the equations that you wrote down for x in a maybe somewhat complicated way, but a way which in principle you could write down. I don't know if it does, if the computer programs really do it, but in principle, you know, Mathematica and Maple and all that, they should just be able to write down this vector space. Yeah.
How do you make sense of what
Yeah, that's a good question. So here I was talking about coordinates. So in the complex manifold case, a coordinate patch means, you know, a little disk, you know, a little ball, and then you have the coordinate functions that make that isomorphic to a little ball inside complex, inside Cn. You have to talk about an étale map. So the coordinates in the algebraic sense are going to be a collection of functions, but which define an étale map from some Zariski open set to affine space. And then the forms are just pulled back from affine space. So in terms of writing things down, it just comes out the same, which is, it's again just on a Zariski open set. If you choose coordinates, it's going to be written like that with algebraic functions here. Okay. Does anybody know if Mathematica or Maxima or whatever will actually calculate the Durham cohomology? Okay, well, anyway, okay. You probably should, but it might be a heavy-duty calculation. Should be able to do it for curves at least. Anyway, so the point here is that then just that this is really an algebraic thing that depends on the equations of x. And so what might seem a little surprising, but it's not all that surprising when you see why, is that this decomposition partially has that property. Okay, so. And that's what's called the Hodge filtration. Okay, so I guess the first thing to say is that we have a transcendental map. We have what we'll call a transcendental isomorphism. Which is the complex Durham cohomology isomorphic to the topological cohomology. This thing here, we'll call this. Right, so this is going to have some Q vector space inside here. this is going to have a K vector space. Right, this is going to have this K vector space here inside it. Has this Q vector space, which is just the rational cohomology. And these are completely different in principle. And the relationship between these two things, so if you take a basis here and take a basis here, then you get a matrix of numbers. Those are called the periods. They're basically obtained by taking classes that you would get over here and integrating them against classes here. So they're things of the form, some integral of some algebraic function over some cycle, basically. So those are called periods. And in general, they're highly transcendental numbers. I mean, they're never, I don't think they're ever algebraic, but there's some special cases when they're kind of close to being algebraic. So like namely a complex multiplication elliptic curve, the periods are still not going to be algebraic, I think, but there's going to be some algebraic relations among them. Okay, so. But so we had this isomorphism with direct sum HPQ, right? That came from this picture. Although it's not really, I mean, it's definitely not defined over Q either. It came from some analysis on the manifold. Okay, so there's not really any reason that it be compatible with either this side or this side. In fact, it's not. However, what we have is we have the Hodge filtration. The Hodge filtration, well, let's just call this Fp of Hi. Let me be a little, since we have this isomorphism, let me just be a little vague about which Hi this was. This is going to be the direct sum R plus S equals I, and R bigger than or equal to P, I think, if I'm not mistaken. It's supposed to be decreasing, so when P gets bigger, it's harder to do that, right? So, okay. So if we take the pieces in the decomposition and take subspaces, which are sums of everything from from one place on to the left or to the right, whichever way you write it. This gives you a filtration. So this is a decreasing filtration. So Fp plus 1 is smaller than Fp. And so the first interesting point is that this is defined over K. So this is called the Hodge filtration. Yeah, sorry. Okay, so roughly speaking, what this means, I mean, I'm just explaining this defined over K thing. That's not really the topic of my talk, but that's supposed to represent the idea of what type of thing you need to do to get that information. So if you have something that's defined over K, that typically means that you'll be able to calculate that information from some calculations using the polynomial equations of X. Okay. Like these integrals, the period, the integral relating these two, you can't just do that with polynomial calculations, right? It's an integral. Okay, so the Hodge filtration is defined over K, and then HPQ is equal to Fp intersect with FQ bar. Because of this property, where did I put that? Because of this property, the complex conjugation, so this bar is the complex conjugation with respect to the real structure given by this Q vector space, okay? So the fact that you can use the Q structure to complex conjugate and you have this thing be defined over K means that, well, the FQ bar is not going to be defined over K or Q or anything, but it's sort of obtained from the one that was defined over K. And the HPQ is something which is obtained by intersecting those two, okay? So it's kind of half, that's why I was saying it's half defined over K, and then the other half is sort of anti-defined over K or something like that. Kind of an interesting little point especially for what we're about to say later, is that we can also do the following thing. We can say, let's let x bar be the variety defined by the complex conjugate equations. And then we have a map we'll call little c from x to x bar, which is just sends, oh, let's call these maybe z0. In homogeneous coordinates, it just complex conjugates all the coordinates of the projective space. Okay. And since we complex conjugated the coefficients of the equations, if you take a point in x which satisfies the equations, and we complex conjugate all the variables, then that's going to satisfy the complex conjugate equation. Okay. This is a homeomorphism. And what we can say is that f bar, this is a little exercise or something. I mean, it's not totally immediately obvious, but not too hard maybe. The fq bar is also the same as c upper star of the fq, I think, if I'm not mistaken, of the x bar thing. So let's just say fq of the hi diram of x bar. So this thing would be defined not over k, but over sort of k bar, which is the complex conjugate version of k. So this is, again, something that in some way is defined over a field, but you have to conjugate it you have to pull it back by this homeomorphism. So you might say that the Hodge decomposition is actually determined by the Hodge filtration, which you can define by equations on x. The Hodge filtration that you can define by equations on the complex conjugate variety, plus you just need to know this homeomorphism of spaces. Okay. We'll see that sort of principle happening a little later. Okay. Now where am I? So that's Hodge filtration. Okay, there's a bunch of stuff which I'm definitely not going to talk about today, but which would be in a topics in a course on Hodge theory, of course, which is like polarizations and stuff. So the Kähler form gives you what's called a polarization of this thing. It's a little complicated. You have to talk about primitive forms and stuff like that, Riemann bilinear relations and so on. It gives you some kind of metric structure on this. In particular, it gives you metrics on these spaces, on these HPQ spaces, and kind of actually the slightly more natural thing is the Hermitian form that's obtained by taking plus or minus 1 times the metric, the positive definite metric. So kind of the natural thing that happens from the polarization is an indefinite Hermitian form, or it's really in this setting it's defined over Q actually. But I'm not going to talk about that. So what I want to look at, so the thing I'd like to look at is what happens when we try to start to look at some less commutative sort of topological invariants, right? So I said here, study the topological invariants. The first topological invariants are just the cohomology, but maybe there's other topological invariants that we would like to consider also. So then there's the question of how that would work. And the first step, so I'm going to do this step in this case, although it was a little bit more motivated by the next setting. But the first step is to transform this situation a teeny bit by what's called the Riesz construction. I think I was going to talk about mixed Hodge structures, but that was actually in my plan. That was after the Riesz construction, so we'll first do this. Okay, it's the Riesz construction. So suppose we have a vector space and a F, a decreasing filtration. Then, let's say a C vector space. Then let's let curly v, finite dimensional vector space. Let's take v tensor with O of the affine line. So this is just a vector bundle of the same rank. On the affine line, which is just C, right, in terms of points. Then we take the following thing. It's not really a sub thing, but it's a modification of this. So then let's look at a new, let me just write this. So let's look at C of V comma F to be defined to be the sum of lambda, and I think this is correct, but it could be mistaken, but I think it's lambda to the minus p times f. Let's see. Okay, so if we have a filtered vector space, then we get a filtered bundle. And we can just take the sum, so to speak, of the lambda to the minus p, fp, where here the lambda is the coordinate on our line. So A1 is spec of C lambda. So there's kind of a slogan here, which is kind of lambda equals h bar, so to speak. In some settings, I'm not sure to what extent that's 100% true, but maybe people could comment if they want or something. But in some way, lambda is sort of h bar for the physics-oriented people. Okay, so this is called the Riesz construction. So really, this is it's really a subsheaf of V tensor the structure sheaf on GM, and we should take, let me not write this, but the I lower star of that onto A1. In other words, this is sections of this bundle that have poles of some order at the origin, because depending on, here I multiplied by possibly negative powers of lambda. Okay, but this is usually a locally free sheaf. Okay. And in fact, also GM acts on, GM, which is C star, acts on this thing, C of VF, over its action on A1. And this, you can recover, so this is an equivalence of categories. So you can recover the filtration from the C of VF plus the action. So depends on why did I say usually? Well, you have to, depends on your definition of filtration. If by a filtration you mean something that starts at 0 and becomes the full space, then that's true. If it started at something which wasn't 0 for some reason, that wouldn't be true. But let's just assume a filtration, we mean a usual kind of filtration. And then that's fine. And so, right, the sections of F, they're just the things where in the frame for this thing, the sections, when you multiply by the action of C star, it's the sections which have a certain order of growth rate when you go to the origin. So if you think about the frame, right, there's a difference of frames. If you suppose, like, if you choose a, let me not write this down, but if you choose a compatible frame with a frame compatible with the filtration, then you get a frame for this bundle just by taking the lambda to the appropriate power times the frame of that piece of the filtration. Okay, and then that piece of the filtration is given by all the functions that have that order of growth as you go to the origin. Okay. this, again, I mean, let's say exercise. So we can think of, the upshot of this is that we can think of a filtered vector space as being the same thing, modulo this usual thing, filtered vector space is really equal to GM equivariant bundles on A1. And if you like algebraic stacks, this is the same thing as bundles on the Artin stack A1 mod GM. You should say a few things on both sides to make sure that we don't have some kind of not good filtrations and so on. Okay. So now we're going to apply that to our Hodge filtration. Okay, so applying this to our Hodge filtration, we get a vector bundle on the affine line with a C star action. Now, one thing I guess, what's the level here? It's like, it should stop here or something, right? Yeah, okay. Well, let me just go over here. There's a different way you can say this. So you can also say, oh, yeah, sorry. This says you can also get this bundle by looking at the family of complexes omega dot x, but instead of taking the differential, you can take lambda times the differential. And so if you like, maybe a better way of saying this would be, let's on x cross A1, and then let's take the PR2 to A1. On this thing, we would have omega dot, let's say x cross A1 over A1. That's the same thing as omega dot x box times with OA1. Then with the differential, lambda times d, the d relative. So you take the relative differential over A1, but then multiply by lambda, so lambda is the coordinate here. Okay. Now you're going to say that looks kind of stupid, which is perfectly correct. If lambda is different from 0, then this complex is quasi-isomorphic to the usual one, right? Because you can just make a quasi-isomorphism, but you'll have to multiply by powers of lambda on the different terms here, okay? And if lambda equals 0, it's even more stupid because it's just equal to 0, okay? But the point is that this gives you a deformation between those two cases. So this is a deformation. Then we should take, right, so then we have the bundle, which is the higher derived direct image of this thing. Okay. And so a little lemma is that that's going to be the same. This thing is isomorphic to the other one. I guess it's a little lemma. I'm sorry about that. I forgot to say one thing, which is that the Fp of H I Durham of X is obtained by what Dulin calls the stupid filtration, the filtration bête. This is the hypercohomology of X with coefficients in the complex, which is omega bigger than or equal to P. So, you need to use this fact. We'll say fact here. This basically comes from the degeneration of the Hodge to Durham spectral sequence. Which in itself comes from harmonic forms on X scalar. So, yeah, sorry about that. I should have said that before. But so this is a kind of classical fact, but using this fact, then it's kind of easy to see that when we do this construction with the complexes, you get the same thing as this psi construction, the Riesz construction. And so now let's just look at what this says. So this says, so we've got this bundle on, let's say this, let's just write it this way. This is a stack. This stack has 2 points, okay? There's the point 0. Let's write it like that. And there's the point 1. So 1 is just a point, and 0 is actually a BGM. Right? 0 is the fixed point of the GM action here. So in terms of the stack, you have a GM action. And the fiber over 0, well, let's do the fiber over 1 first. But this just means, plug in lambda equals 1 or lambda equals 0. I mean, this is just saying what I was saying before, that either lambda is different from 0, in which case it's equivalent to lambda equals 1. That's just the usual Durham complex. So the fiber over 1 is just the usual Durham cohomology. And the fiber over 0 is the associated graded. Which is defined to be the direct sum over all the different p's of f p mod f p plus 1. And this has a C star action. So GM acts, I guess I'm going to get this one wrong, right? Tempted to say minus p probably. Well, not sure. Sorry about that little calculation. Well, GM acts by one of these two, either t to the p or t to the minus p on these pieces, okay? So the fact that you have a stack here, which is a BGM, it means that a bundle over this thing really is it's a vector space plus an action of the multiplicative group. That action of the multiplicative group decomposes it into a direct sum of pieces, and those pieces are the graded pieces of the filtration. Okay. And this is actually what's called the Dolbeau cohomology, which is just the direct sum over P and Q of H Q of X omega P. So this is what you get when you put the differential equal to 0. Okay. So the Dolbeau cohomology, right? The way you see that, roughly speaking, is that it's going to be the direct sum of the harmonic PQ forms, but for the del bar Laplacian. And the Kähler identities tell you there's an equivalence of Laplacians up to a factor of 2, and so the PQ forms for the del bar Laplacian are the same as the ones for the usual Laplacian, and so that's why you have this direct sum decomposition. Maybe I should probably put this up here. I was sitting over there in the conference last week, so I know all about the, the thing in the middle here. Okay, so, but we're up there. Okay, so that's the Reese construction. Oh, let's see, now where are we? Oh, sorry, but we haven't really done anything all that, how are we doing? We haven't done too much yet so far, but what we can do is we can take the Reese construction and combine it with the F bar. So let's just call F tilde equals F bar, but it could be a different filtration, okay? So in our case, it's the bar, but let's just we're not worrying too much really about the analysis here. So let's just suppose we have some other filtration. Then we can do a C of V F tilde on A1, but we think of A1 as being the other neighborhood of inside the projective line. So it's the neighborhood of infinity. Okay. And now you can see that this C of VF restricted to GM is just V tensor O GM, which is also C of V F twiddle restricted to GM. And so we can, by using this isomorphism, we can glue them. And we get a bundle C of V F twiddle over P1. And it's GM equivariant. Now we have our two filtrations. So F and F twiddle, if we take the F twiddle equals F bar, the two filtrations are what's called I opposed. I equals, yeah. What does that mean? It means that, in other words, if we put HPQ, if we define HPQ to be HFP intersect F twiddle Q, then our space, let's call this V, sorry, VPQ, then our space V is a direct sum of VPQ. If you just take two different filtrations, they might be opposed or not, but you might have combined a 2 opposed and a 3 opposed and a 0 opposed and a -1 opposed filtration. There's no reason for two arbitrary filtrations to have this opposed property. Okay. And the lemma is that the F and F twiddle are I opposed if and only if this psi of VF F twiddle is semi-stable bundle of slope I on P1, which is to say it's isomorphic to a direct sum of copies of OP1 of I. You know the Grothendieck theorem that all the bundles on P1 are direct sums of the standard line bundles. And this condition says that, well, the only ones that occur in that bundle are the ones at degree I. Okay? And if you think about it, that's equivalent, again, let me just leave that as an exercise. That's equivalent to this I opposed condition. You could just do that on each piece here. Sorry, I should say. Sorry, the key thing here was we want P plus Q equal to I for that decomposition. Okay, so now that's going to be sort of the key to our technique for interpreting this Hodge theory information in a kind of a geometric way, right? So we've done this already, right? So in some way, the rest of the talk is just kind of going a little further in that direction. So Definitely wouldn't say I'm finished here, but right, we've given a geometrical interpretation of this bundle, right? Here we started with the filtration, but suppose we don't start with the filtration, right? Then we said we can just start with this complex of differential forms. You know, again, this is the complex of algebraic differential forms on X, so you need to use that Gaga theorem. But we can just look at this complex of differential forms and just twist it by multiplying the differential by lambda, then looking at what happens when lambda tends to 0. You get this deformation, which in this case happens to have the property, which of course is not usually going to be the case, but in the Hodge theory case, a compact Kähler manifold and so on, that's going to have the property that when you do that, you get a bundle anyway. Right, generally speaking, this thing will be maybe a quasi-coherent sheaf or something like that if you don't know the Hodge theory property. Okay, but anyway, but as far as the construction is concerned, we've just given a completely algebraic construction of this thing. Then we needed to use this isomorphism. That isomorphism, if you think about it, comes from this thing here. Where are we? That can be viewed as coming from this situation here, basically, where you take the complex conjugate variety and you identify them. And so then you combine that and you add in the same geometric filtration on the other side, and you get to this property of the filtration. Okay. So now let me go a little faster. So what about mixed Hodge structures? So if X is, so I said X was smooth and compact, smooth and projective, so it's compact. If we don't make those hypotheses, so if X is not smooth, and quasi-projective, then you can still define the Durham cohomology of X. But then this is going to have what's called a mixed Hodge structure. I mean, it still has its filtration. But it also has, and therefore it has the FP bar. It also has what's called a weight filtration. So this is an increasing filtration. This is by Dooley. If you haven't looked at this already, I would definitely suggest reading the paper Hodge 2. Hodge 3 also, but it's a little more difficult to read. Hodge 2 is definitely very readable. It has what's called a weight filtration, and this is defined over Q. So when I say Q here, I don't mean that X might be a variety defined over Q. That we're using capital K for that. I mean the Q which comes from the topological cohomology. Okay. And then what we get is we get the induced filtrations on the GUR I, W are I opposed. This is called a mixed Hodge structure. And we can view that in terms of the Rees thing. It means that arc C of V F F bar is becomes a filtered bundle on P1, filtered by the Wi of the C, which is C of Wi V FF bar, and has this property. The GER WI of this Xi thing is semi-stable of slope I, i.e. Okay. And let's call this condition, so, you know, it also has the other condition, which is it also has a GM action. Plus, I mean, I'm being a little bit, I'm not really making too much of a distinction between the fact that it's F bar, which was the complex conjugate, and it had a rational structure, or just some other filtration, but anyway. But actually, we're actually going to drop that whole thing. So let's just keep star. So drop this double star condition, and keep star, and we'll call that being a mixed twistor structure. So what's a mixed twistor structure? An MTS, so is a filtered bundle with an increasing filtration such that the GER IW of V, a filtered bundle on P1, such that the GER IW of V is semi-stable of slope I. Then you can sort of, there's a theorem, so there's, so Deligne's theorem, so in the paper Hodge 2, the main theorem really in this paper, you know, aside from the construction and everything, where did I put that? I guess it's up there. The main theorem of that paper is that there's something called a strictness property for mixed Hodge structures. And the proposition is that M mixed twistor structures satisfy Deligne's strictness property. Basically, this is because of the fact it's just the strictness property of semi-stable bundles, right? If you have two semi-stable bundles of the same slope, you have a map between them. That map can't sort of vanish an extra amount at some points. I mean, it might have a kernel, it might have a co-kernel, but the kernel and the co-kernel are also semi-stable bundles of the same slope, and the rank of the map stays the same at all the different points. Okay, and that property basically, I mean, you have to maybe translate that a little bit, but that basically tells us that you have this strictness property. And you can actually give a proof of Deligne's proof in Hodge 2 is with a bunch of filtrations and stuff like that. You can actually give a geometric proof using semi-stability. I mean, it's kind of equivalent, obviously, but you can give a proof using just properties of semi-stable vector bundle. Okay, so that's mixed Hodge structure. Okay, now what do I want to say next? We're getting a little behind time here. But.
The strictness property that leads to being
Yeah, so that's an abelian category. Yeah. Thank you.
And is star independent of F?
Yes, that's what I'm trying to say here. I mean, that's why I rewrote this definition, because here this had the F in it, but the property star, it just depends on having a bundle plus a filtration by subbundles. You want them to be subbundles, I mean. Okay. Yeah, and so, thank you, Patrick. That, among others, I mean, the strictness property says a teeny bit more, but basically says that's an abelian category. Okay, so now the question, what about higher homotopy invariance? Or like other, you know. So the classical one, so right, so the question is really what kind of things can you apply Hodge theory to, what kind of topological properties? So really what we saw at the beginning is really the crucial thing, which is that whatever's happening, the Hodge theoretical thing that's going to be happening is on a complex invariant. It's on a complexified invariant. Okay. Whereas, for example, the weight filtration would be a kind of a rational invariant, but once we go to mixed twistor structures, we've kind of forgotten the rational structure, really. But let me just, so recall, let me get my piece of paper here. Like, you know, really the first main ones were rational homotopy theory. Which in the topological case, you know, is due to Coulomb and Sullivan. And then there's the Deline, Griffiths, Morgan, Sullivan paper, which applied that to algebraic varieties. But I mean, which said stuff about algebraic varieties in any case. But so these give you other invariants of the topology. They're defined over Q, let's say maybe, but then you can complexify and you get a mixed Hodge structure. Either the case of simply connected or the Malcev completion of a nilpotent fundamental group was done by Morgan-Hain. And then the case of what you call the relative Malcev completion was done by Hain. And kind of similarly, but this is maybe a little later, but you can also do a mixed Hodge structure on the local ring of the character variety. This is really very closely related to this Malcev completion, relative Malcev completion thing. But this is sort of due to Goldman and Milson. I mean, it's used as the technology in the paper of Goldman and Milson. Then we wrote a paper with Philippe Eyssidieux and myself. And if I can, I'll just be able to explain that. We might just get there. So I guess I really totally don't have time for the next section, but
Sorry, could you just say GGNS?
Deline, Griffiths, Morgan, Sullivan. Sorry. It's a differential graded mixed structure. I mean, it's also a differential graded mixed structure, but yeah. Okay, so now this is the topic of this would be the topic of another talk, obviously, but then we have the Hitchin hyperkähler structure. On the character variety. Now the Hitchin hyperkähler structure on the character variety. So let's let M equal let's say M Betty. Well, just M equal the well, yeah, I guess we want S equivalent. So let's take the moduli space of representations of the fundamental group, which it's the representations of pi 1 into, let's say, GLN and C modulo S equivalents. And then we have Hitchin defines the moduli space. I mean, Hitchin's equations define a homeomorphism. It's real analytic on the smooth set between M and let's call it MH, which is the moduli space of Higgs bundle. Semi-stable, CI equals 0, etc. Okay, and so this should be compared with the M de Rham space, which is the moduli space of vector bundles with an integrable connection. Let's call these E also. Okay, so just the kind of really quick point is that this is some kind of H1 of X, de Rham cohomology of X with coefficients in GLN. This is some kind of Dolbeau cohomology. And this is some kind of topological cohomology. Roughly speaking. So now we're talking about non-abelian cohomology, right? We're talking about cohomology with coefficients in this non-abelian group. And so what does Hitchens say? Hitchens says that actually, so there's two different complex structures here. So this is complex, but this is only real. So there's two different complex structures here. There's the complex structure of these two things. Then there's the complex structure of this space. And what Hitchens says is that those are actually part of a quaternionic structure. So it's a delicate question, and I'm not sure we really understand this very well. What would it mean to have a quaternionic structure on the singular points of a manifold? But for now, let's just say on the smooth points of this manifold. So typically, if X is a Riemann surface, which is really the only case where we have really good examples of this, in the case where X is a Riemann surface, then there's a big open subset where the space is smooth, and it's even completely smooth in the case where you look at representations that have that they're not flat, but they're projectively flat, and whose degree is co-prime with the rank, and so on. Okay, but so now, sorry for speeding up here. So the point is that when you have a quaternionic manifold, you get what's called a twistor space. That's where the terminology over there comes from. I mean, that terminology comes after this terminology. You get what's called a twistor space, which is M cross P1 with a whole bunch of complex structures. So let's call this kappa. This is a little kappa. Right, so when you have a quaternionic vector space, you have this space of complex structures in the quaternions. Well, it turns out if you calculate, there's no one in the complex structure. And having a complex structure is some linear combination of I, J, and K, with the property that the sum of the squares equals 1. That's the two-sphere. That is naturally identified by the homeographic projection with P1. And it turns out that you get a complex structure on the total space. That's not like immediately obvious because you have to check that the two are compatible. But if you, on each fiber, M cross some point of P1, you put that complex structure. That gives you a complex structure on that fiber. In the P1 directions, you just use the complex structure of P1. That gives you a complex structure on the full twistor space, okay? And the point is that now we can say that the twistor property which is really equivalent to the quaternionic property, says that if you take the normal bundle, so if you take fix a point in M smooth, let's say. Fix a point in M smooth and look at that P1, okay? Let's call this P1 row. That's what's called a preferred section. The property is that the normal bundle to the preferred section has exactly our property. So the normal bundle to the preferred section inside this M cross P1, that's the same thing as the relative tangent space restricted to the P1. This is semi-stable of slope 1. Okay. So you'll recognize that property over there. I mean, of course, this came first, and then that sort of generated these kind of generalizations. But so this is a sort of a weight 1. We'll call it sort of a weight 1 mixed weight 1 Hodge structure, like Nonabelian. Hodge structure. Okay. It's actually an immediate corollary for the smooth points that the family of completed local rings has a mixed twistor structure. This is again an exercise. If you take the local rings of the M cross P1, let's say over along the section, take the completed, the family of these things over P1, I think it's W minus I equals the ideal to the I plus 1 maybe. Maybe there's a plus 1. Anyway, define the weight filtration to be just the powers of the ideal. Okay. Then this thing is a mixed twistor structure. This is actually completely immediate from this property in this case, because really the GER W is just sim I of the GER W1. The GER W1 is, let's see, maybe GER minus I, GER minus 1. And this thing is the dual of the normal bundle. So we have this filtration, and we know that the associated graded is the isometric power of something which is a semi-stable of slope 1. I guess this is, the dual is slope minus 1, sorry. So it follows that the GER minus anything is just going to be the symmetric power of this bundle, and it's again going to be semi-stable at slope 1. So this is actually easy. So of course, the hard part in the theorems about having mixed twistor structures is really that there's many points where the moduli space is singular, and then you have to work more in that case. But for smooth points in the moduli space, this is just automatic. Anyway, so I should just finish here in 10 minutes. Sorry about the timing here. Then what were we trying to do with Ludmil and Stony? So the project with let me describe briefly the project with Katzarkov and Pantev. Let me just, before saying that, so I don't have time, so sorry, Bertrand. You can ask Bertrand, who's in the back of the room. I don't have time to talk about the, this was generalized to some extent, I mean, sort of, new developments. When I say new here, the new developments were in the 2000, 2010 range. This was in the late 1990s, but anyway. The new developments were by Katzarkov-Pantev-Toen and Pridham on Hodge structure, like mixed Hodge structure or mixed twistor structure on schematic homotopy types. The idea is that the sort of, this was really, we were discussing during the conference during the week how both Stony and but also Ludmil are actually very stubborn. So they sort of say, okay, now we're going to do this, solve this problem, and you just sit down and think about it for a long time and then make a little bit of progress, and then you think some more and so on. The basic idea is, can we generalize this? Can we generalize this situation to something that would involve sort of higher homotopy groups, but mixed with these character varieties in some way? And in a way which would, for example, recover the results on rational homotopy types, for example. Let me go back over here. So what was the idea of what we were trying to do with Ludmil and Stony? The idea was to say, okay, this H1 here, if we say H1 of X top, let's say, with coefficients in some group, this is really some kind of pi 0 of some kind of mapping space from X top into BG. Okay? And so to get kind of higher invariance, you would want to replace BG by some kind of higher stack. Now, why do we need stacks? Because you could say this is okay, we just can look at spaces and so on. If G is a group, then BG is a space. And a higher stack is really just kind of put any space here you want, basically. If you take any space but whose fundamental group is G, then you'll have sort of a higher stack, so to speak, or a higher space lying over the BG. However, one of the main points is that Hodge theory talks about complex invariance. So in the case of, for example, rational homotopy theory, you kind of get around that because you can take the rational homotopy groups, which are rational vector spaces, and just tensor them with C, okay? Then you can say, okay, now I can put a Hodge structure. Remember that the pieces of the Hodge thing, they have periods involved in them, which are transcendental numbers. So you can't get away from having these complex things. And so here, here you can see this was H1 with coefficients in a complex group, right? You can say some stuff for real groups, for example, but you don't get quite as nice a twistor space picture, for example. I mean, that's of course very interesting, but you really want to first look at complex invariants. So what's a complex invariant going to be? So we need a theory of what you might call spaces, parentheses like BG, over the complex numbers. And this is the idea of schematic homotopy types. That's sort of Bertrand's language for that. Well, this really comes from, I think, Grothendieck in Pursuing Stacks at some point says that. And there's a paper by Breen and Ekedal, I think, about the schematic sphere, if I'm not mistaken. Kind of early. Oh, let me just profit. Sorry, I almost forgot to say this. So Clark Barwick, who gave a talk, if some of you might have seen it, about the factorization algebras, all he didn't get to factorization algebras, on the Farg-Fontaine curve. He assured me that the Farg-Fontaine curve at the prime, so he's talking about Farg-Fontaine curves at primes, P. He said the Farg-Fontaine curve at the place at infinity is supposed to be the twistor line, supposedly. Don't have the faintest idea what that would mean, but anyway, it's a little advertisement. I don't know if that's really true or not, but I had sort of heard people say something like that. Anyway, so we'd like to have, anyway, sorry for that little ad interlude. So we'd like to have a theory of spaces over C, which is to say some kind of schematic homotopy types. And the idea is just to look at let's say higher stacks on the side AF C of affine C schemes. Let's say a finite type or something like that. So we'll just call this such a stack T. So basically it's just a presheaf of spaces. F C op is just C alg. Commutative C algebra. We just look at functors into spaces, roughly speaking. Then there's some kind of descent condition and so on. These days actually we actually have access to a ton more technical tools for this type of thing than was available a while ago. So let's just, roughly speaking, we think of this as a functor like that satisfies some kind of stacky descent condition. And then the pi i's of T are just the sheaves you get a presheaf, which is, these are the simplicial presheaves. Then you can take the homotopy groups, you have to have a base point and so on. You can take the homotopy groups of the presheaf and then sheafify them. Those are the pi i's. Then so you want to make some kind of requirement, right? So if you go back, this is kind of our guide, right? So here, this is a reductive group scheme, right? Or at least a linear algebraic group. So we might want to ask that pi 1 is to be a linear algebraic group. Now the pi i's are supposed to be commutative. And when you look at this a little bit, there's actually a tiny bit of work about higher cohomology with coefficients in GM. It doesn't work very well, and we need Gaga theorems, as we saw at the beginning. Those are not going to be true in that setting. So you'll have trouble passing between the algebraic and the analytic situation. or you could try an abelian variety or something like that. That's not a good idea. So the pi i's, for I bigger than or equal to 2, the pi i's should be some kind of unipotent group schemes. Abelian. So what I'm kind of not saying here is that you might have a situation where the pi 0 is itself some kind of scheme or something like that, and then this is sort of over that. So these pi i's might be sort of group schemes over the base or something. Yeah, I guess time to stop. So let me just say, so what we did with Ludmil and Stony in our paper called Nonabelian mixed Hodge structures is we sort of came up with some conditions. So in the paper Nonabelian mixed Hodge structures, it's just a preprint. We came up with some conditions on a T with a filtration F, let's say an R structure maybe, filtration W defined over R. So we've really seen what these filtrations, F, T, when you talk about a filtration in the non-abelian setting, you really mean a family over this stack A1 mod GM. Okay. We came up with some conditions on these things such that conjecturally, underline conjecturally here, that if T satisfies those things, then we can define a mapping stack from X into this T thing that also satisfies them. Okay. And we checked this in one case. We checked this for I'm not sure what kind of brackets to put here. T was the kind of the motivic homotopy type or something like that of the projective line. Okay. And so let me just finish by saying that in the case of a simply connected X, for example, for X simply connected, and if we say let's restrict to T also simply connected, then the rational homotopy type is kind of the universal such T. This has to be taken with some grains of salt, which is to say, the rational homotopy type is going to sort of be infinite. So it's really, this is going to be the pro, maybe. It's going to be a pro object. But it's sort of given by the limit, the homotopy limit, over maps from X to T of T, basically. And so this was supposed to be, I mean, I don't think this was necessarily all that successful, but maybe this is like a little bit of a reading guide if anybody's interested to look at that. So there's these other versions of the theory. Where did they go? Did I erase them? Yeah, Katzarkov-Pantev-Toen and Pridham about mixed Hodge structure, mixed twistor structure on schematic homotopy type. Let me just say none of this is really completely satisfactory because you have a basic problem. That's why I wanted to talk about next, but I won't be able to. You have this basic problem of the fact that in this twistor space picture for the Hitchin moduli space, you have these preferred sections, but the preferred sections are kind of uniquely associated to points of the original moduli space in that case. Whereas in the case of when you have higher weights, a point of the moduli space might have several different preferred sections that go through it, or what you might call preferred sections. And it seems kind of unclear how to, but the property you can see here is really localized along the section. So that's like the thing I can't figure out, which is how do you integrate that stuff together? You have a Hodge kind of a property that's going to be localized along the section, but the sections don't really correspond to points of the moduli space anymore. And so I kind of have been investigating that in a really basic first case, which is the case of local systems on an open curve, which you can see in the preprints that I posted like last month and last year. Anyway, so I'll stop here.
Questions for Carlos?
You're speaking about flat bundles, connection.
Flat.
And you somehow move to arbitrary bundles, right?
Yeah, sorry, I just didn't have time. I skipped something important here, which is that I guess I should have put a little dot here. This x dot is sort of composed of an x Betty and an x Durham and so on. The x Betty, this is the stack which to every C algebra associates just the space, the constant space x top. So this is the constant sheaf. But this x Durham is the thing which is defined by x Durham of A is equal to x of A reduced. This is the thing with the property that the maps from here into something are going to have a flat connection, basically. So these are flat. These are supposed to be maps which have a flat connection in that sense. But there's sort of two components of this. I was going a little fast here. There's supposed to be this T thing is supposed to have on the one hand a sort of a Betty side which is defined over R, but on the other hand a sort of a Durham side which has the filtration F. And for this map, for the Betty side, you use the map from x top, the constant stack whose values are x top. And for the Durham side, you use this sheaf here. On the Durham side, maps from that, maps from this sheaf into BGLN, those are going to be flat connections. Maps from this thing into BGLN are just going to be local systems. And then there's a Riemann-Hilbert isomorphism that you need to use to compare these two and glue them together, basically. So yeah, but good. That's a good point.
My question was simpler because at the top line, at the top left bullet, you're just talking about arbitrary bundles. So it's used not G, right? But functions, sheaf or function would be G, right?
Up here?
Yeah.
No, that's x top. A map from x top into BG, that's a flat bundle. That's a flat G bundle. Flat, yeah.
But do you have less on that?
No. This is B. What is this BG? This BG. It's not the topological BG. It's the thing which it's the thing whose values. So BG of a sheaf A is defined to be G of A discretized. Okay. So it's not really G discretized because it depends on A in this way. But as a space, as a space it's discretized. So
The left-hand side you really have G, not sheaf function. Say G. So in H1, it is G, not function. It's very G.
well, again, it's the same G. It's the G which is a stack. It's a group scheme, but then viewed as a sheaf where on each thing you give it the discrete topology. So it's not. That's not the fact that this is a linear algebraic group is not generating any kind of topology which interacts with this topology. There's no interaction. Yeah. Okay. But good point. Thank you. There was another question. Yeah.
Maybe this is what you were mentioning at the end with mentioned something about parabolic bundles.
Yeah. Okay, so it's the parabolic structure which accounts for the fact that a given point in the moduli space might have several different preferred sections that go through it. The preferred sections that go through it, those are determined by the parabolic weights, basically, of the local system at infinity. Essentially, due to the fact, I'm sorry, this was, I also wanted to give an example of a mixed Hodge structure, which is if you have like an open curve, then you have a weight 2 part, which corresponds to the punctures. And it's that weight 2 part on the punctures which tells you that you have kind of a more movable space of preferred sections. You can sort of see that here. Where did I put this? Suppose you put an O of 2 here instead of O of 1. Here I'm also skipped over the fact that we're looking at involution invariant sections, but the involution invariant sections of this thing are rigid, so to speak. But if you take O of 2, then H0 of O of 2 is 3-dimensional, so the involution invariant sections are R3 instead of R2. And yeah.
More questions?
Yeah.
In the Hitching case, the preferred section, how do you describe the preferred section?
Well, in this picture, I'm again skipping some stuff here about Deligne gluing and so on. But but if you just look in Hitchin's paper, he just says you take the manifold and you cross P1. The manifold has a hyperkähler structure. You take M cross P1, that has a complex structure. But where the complex structures on the fibers, they vary. Right? They're given by I, J, K, and so on. And the preferred sections are just, what did I say? It's a point cross P1. Well, whichever point you start with. There's one preferred section for every point of M. Yeah. That's what I'm saying. But this is fundamentally related to the fact that this has weight 1 here. If you had weight 2, you'd have like lots of sections for a given point of M, basically. Does that answer?
Thank you, Carlos. Yeah.
Okay.